Hey everyone, it's Dr. Garner here. In this lesson, we're going to look at energy. So energy is an abstract concept, but broadly speaking, it describes the capacity to do work and to transfer heat. So broadly speaking, energy is what makes things happen. We can measure energy in terms of joules. So this is the SI unit that's typically used to measure energy. It's abbreviated with this capital J. And a joule is defined as being a kilogram times a meter squared divided by a second squared. So it's another example of a derived unit. It's made by combining a number of SI base units together. So energy fits into two categories. So energy is either classified as kinetic energy or potential energy. So kinetic energy is the energy that's associated with an object's motion. In contrast to that, potential energy is energy that's associated with an object's position. We're going to see a couple of examples of each of these later on in the lecture. So one of the most familiar examples of potential energy, at least, is that of gravity. So gravitational potential energy, the energy associated with how far something is from the Earth's surface. So let's take a look at an example that shows this. So in this cartoon, I'm showing a hill. And you can imagine this hill if I had a ball rolling towards it. So let's look at this situation. So of course, this ball, it's in motion. So of course, it's going to have some amount of kinetic energy associated with its motion. And it's on Earth, so there's some amount of potential energy associated with how far it is from the center of the Earth. And as you guys know, if you pick something up, you have to put in energy to lift it away from the Earth's surface. If you let an object down, it's attracted to the Earth, so it goes back down on its own and releases that potential energy and accelerates towards the Earth's surface. So what we're going to do is we're just going to graph the kinetic energy and potential energy of this ball as it rolls across this hill that we're showing in this cartoon. So again, we have our ball rolling towards the hill. As it starts to go up the hill, it's going to slow down. So it's slowing down, so that means that it's going to have less kinetic energy than it did before. And as it goes up the hill, it's also going away from the Earth's surface. So it's going to take energy to move it away from the Earth's surface to allow it to get further from the center of the Earth. So what's happening as the ball's rolling up the hill is that its gravitational potential energy is increasing as it's going towards a higher altitude, further away from the Earth. Its kinetic energy, however, is decreasing. So it's slowing down as it moves further from the Earth's surface. So what's happening here is that the kinetic energy that the ball is losing is being converted into potential energy as it moves further from the Earth's surface. Of course, the ball will continue to slow down as it moves towards the top of the hill, but once it crosses the top of the hill, we'll start seeing the reverse happen. Now the ball is going to accelerate downwards as it moves closer to the Earth's surface. So it's losing potential energy because it's moving closer to the Earth, and it's gaining kinetic energy as it's accelerating down this other side of the hill. And of course, that kinetic energy that it's gaining, it's coming from that lost potential energy. So we're converting potential energy into kinetic energy as the ball accelerates down the hill. On the other side of the hill, it's going to continue, of course, accelerating, and assuming that there's no friction or air resistance or anything like that, at the end of this experiment, our ball should be moving at about the same speed as it started at. So what we see here is that the sum of kinetic energy and potential energy remained constant throughout this process. This is an example of the first law of thermodynamics, which states that energy is never created or destroyed, only converted between forms. So that's what happened here. The total amount of energy, the sum of kinetic and potential energy, remained the same for this ball throughout, but it was converted between kinetic and potential energy throughout the process, but the total sum stayed the same. All right, so it's often useful in chemistry to describe what we call a system and its surroundings. So we can define a system as just any subset of material that we're interested in studying. So it's whatever material you're interested in examining. The system is distinct from everything else in the universe, which is described as the surroundings. So the system is whatever it is you're interested in studying. The surroundings are everything else that exists in the universe. So the energy contained within your system is defined as being the internal energy, and this is abbreviated with a capital E. So internal energy is the total energy contained within your system, whatever material you're interested in examining. So it's the sum of kinetic and potential energy within that subset of material. This value of E, of internal energy, it can change as energy is transferred into and out of your surroundings or into or out of your system. And this change in energy, this is known as delta E. So whenever you see a delta, this uppercase Greek letter delta in chemistry, this describes a change in some term. So it's always defined in the same way. So anything with a delta in front of it, it means the final state minus the initial state. So in terms of your internal energy, a delta E, or a change in internal energy, would be defined as your final energy, so the energy of your final state, minus your initial energy. So we can imagine a couple of situations here. You can imagine a case in which we started at some high energy initial state. Here we're just plotting the energy levels of two systems on this y-axis here, that's energy. So in this example, we started at some high energy initial state and ended at some low energy final state. So we went down in energy. We had a negative change in energy. So delta E here was negative. Energy went down during this process. And that should make sense given our formula over here. If we start at, let's see, a high energy initial state and ended at a low energy final state, our value here, our final energy would be low. Our value here, our initial energy would be high. So small number minus a big number, it's going to give us a negative value of delta E. So energy was, our delta E here was negative. So that means that our system lost energy to its surroundings. You can imagine the reverse of this as well. You could imagine starting at a low energy initial state and then gaining energy from your surroundings to reach a higher energy final state. That would be a positive change in energy, a positive delta E. So energy increased during this process. And again, that's consistent with this equation. If we have a high energy final state, so a big number here, minus a low energy initial state, so a small number here, big minus small, that's going to give us a positive value of delta E. So internal energy can either increase or decrease as energy either exits or enters a system. All right, so gravitational potential energy is a fairly familiar example of potential energy, but it's not all that relevant on a molecular level. So gravity is not particularly important for explaining the behaviors of molecules. It's just not really critical at that size scale. Instead, the force that's most important on a molecular level is that of the electrostatic attractions and repulsions that take place between two charged species. So the potential energy that's associated with interactions between charged objects is described by the equation that we're showing here, Coulomb's law. So Coulomb's law describes this potential energy as a function of the charges of the species that are involved, as well as the distance between those charges. So here our electrostatic potential energy, E sub EL as we've abbreviated it, is equal to a proportionality constant K. Don't worry what the value of K is, you're not going to need to know it, at least not in this course, times the charges of the two species that are interacting, so Q1 and Q2 represent the charges of the two interacting species. For example, if these were a proton and an electron, Q1 might be positive 1 and Q2 would be negative 1. And then on bottom of the fraction here, R is an abbreviation representing the distance between the two charges that are interacting with each other. So we can graph this equation and get some sense of what this means. So what I'm going to do here is I'm going to plot our electrostatic potential energy as a function of the distance between the two interacting charges. And we're going to look at two cases here. We're going to look at a case where we have two particles with the same charge, and then we're going to look at a case where we have two particles with opposite charges. So two particles with the same charge, that might be something like two protons or two electrons. In this case, I'm going to use two protons as my example. So in this case, they both have charges of positive 1. And what I'm doing here is I'm just graphing my potential energy as a function of the distance between these two charges. So these values of +1 and +1, they would go into this equation in place of Q1 and Q2. This value of R here would go in place of R here. That's what we're graphing here on the x-axis. So as you can see, if we put larger values of R into this equation, this fraction is going to become smaller and smaller as R becomes larger. And what we see is that this graph approaches 0 as we move towards larger distances. The other thing that you'll note here is that since these values of Q are positive, and since R is always positive, and it turns out that this proportionality constant is positive as well, then that means that this value of E is always going to be positive too. So this graph is positive at all points, and it's highest when R is small, and it becomes smaller, it approaches 0 as R becomes larger. All right, and this should make some sense given what we know about how particles attract and repel each other. If we have two particles with the same charge, they're going to repel each other. So they're going to try to get as far away as possible. Their lowest energy state is going to be when they're far away. So systems tend towards their lowest energy state. So it makes sense that for these like charges, their lowest energy state would be when they're far apart from each other. So that's what we see here. So the lowest in energy they can be is when the distance between them is very large. They're highest in energy when they're close together. All right, for the other case where we have two opposite charges, we see a graph that's pretty much a mirror image of this. So it's reflected here across the x-axis, and we have something that has the same general shape, just sort of turned upside down. So in this case, in this example, we have a proton interacting with an electron. So here our value of Q1 is still +1, but our value of Q2 is now -1. So that changes things a bit, right? So now, since this is positive and this is negative, that's going to make this value of E always negative. So that's why this graph is always below 0 at every point along the curve. It has a negative value. All right, so that's what sets it apart from the other graph. We still see the same general behavior, though. As this value of R becomes larger, this fraction is going to approach 0. So we see the same thing here. We're moving towards 0 as we increase the value of R. Of course, the difference is the direction that we're coming from. In this case, we're coming from a negative value, from a very low energy, and we're going up towards 0 as we approach 0. So in this case, our lowest energy state is where our proton and electron are really close to each other. And that makes sense because we know that opposite charges attract each other. So it makes sense that if they're going to tend towards lowest energy, that lowest energy state would be the state at which they're close together. And that's what we see here. So the lowest energy state for two opposite charges are when they're close together, and you would have to put in energy to pull them apart to reach a higher energy state. For our two like charges, the lowest energy state is when they're far apart from each other, and you would have to put in energy to push those two charges together since they're repelling one another. All right, let's try out a practice problem involving Coulomb's law. As usual, you should take a moment, pause the video, and try to think through this problem on your own. Once you've finished, or once you have gotten stuck, unpause the video and take a look at the solution. All right, in this problem, we're being asked to arrange these three pairs of charged particles in order of increasing electrostatic potential energy. So we're given these three pairs of particles, 1, 2, and 3. We're told that in each case, the distance between the charges is the same value. It's this value d, whatever that might be. We're also told that the sign and magnitude of the charge of each species is indicated. So like, for example, here, the charge of the species would be -3, and this would be -1, and so on. All right, and they want us to rank these pairs in order of increasing electrostatic potential energy, so lowest energy to highest energy. All right, and they also give us Coulomb's law down here so that we can work out what those values of potential energy might be. I'm just going to move this over to the side here so that we have a little bit of room here to work these out. All right, so what I'm going to do is I'm just going to plug in these values of charge as best I can into this equation and see if I can compare these potential energy values that I get out. Let's do this for pair 1 first. So for pair 1, the values of Q1 and Q2, I know these values, so I can plug those in here in place of Q1 and Q2. I don't know the value of K, I just know that it's some constant, but it's going to be the same constant for all three pairs. I also don't know the value of R. All they tell me is just that it's some distance, d, but we know that that's the same distance for each case as well, so it's going to be the same value for each of these three pairs. So I can just plug in everything that I know here. So for pair 1, my electrostatic potential energy is going to equal that proportionality constant times Q1, which had a charge of -1, so I'll put that in here, times Q2, which has a charge of +1, so I'll put that in here, and then divided by my value of R, which they just tell me generically is some distance d, so I'll stick that in here as well. All right, if I work out the math here, multiply -1 times +1, that's going to give me a -1 times k over d. So my electrostatic potential energy here is -1 times k over d, whatever those values might be. All right, I can do the same thing for pair 2. In pair 2, Q1 has a value of -3, and Q2 has a value of -1. So if I multiply those two values together, that's going to give me a value of 3 times k over d, so +3 times k over d. We can do the same thing for pair 3. In pair 3, my value of Q1 here is -2, and my value of Q2 is a +1. So I can plug those two values in place of Q1 and Q2 in my equation for Coulomb's law. When I multiply these together, I get a value of -2 times k over d. At this point, all I need to do is just simply compare these values to one another and arrange them in order of increasing energy. Now, it's not referring to a magnitude here, so it's not the absolute value that we care about. We want the smallest number would be the negative value, the largest number would be the positive value. So the number that's furthest from 0 in the negative direction would be -2. That's our smallest number of the ones that we have here. And then -1's higher in energy than that. And then 3 is the highest in energy of any of these. And again, we don't know what k over d is, but it's the same for all three pairs, so we can compare them just based on that coefficient that comes in front of them. All right, so -2 is our lowest energy, so that needs to come first. Pair 3 is the lowest in energy. And then the -1 was in the middle, so pair 1 is in the middle. Pair 2 with its value of 3 times k over d, that was the highest in energy, so pair 2 is going to come last. All right, we'll stop this video there. I'll see you guys in the next one.